Welcome to the conference. Welcome to the session. All right, yeah, looks like I'm going to have these glitches from time to time. What I found, interestingly, I'm on one of the latest MacBooks, and many projectors have issues with Macs that run on Apple M1 processor. So I think it will take some time before the firmware gets upgraded. So this is not the worst scenario, like if we get my slides lost for a few seconds. So the topic for today, how Java litters beyond the heap and what we as application developers can and cannot do about that. This talk is about garbage collection, but it's not about the garbage collection on the Java level. Because I do believe that all of you who are sitting in this room have already become skillful in selecting garbage collectors and tuning them for your application workloads. Instead, today, we are going to see what's happening in the nearby neighborhoods. Because Java application usually runs on, it doesn't work in isolation. When you create an application or microservice, it uses a database to store data, to get data from. And those databases also have to run on some physical hardware, such as SSDs. And not everyone knows that garbage collection as a technique is widely used by other successful projects, including Postgresql database, including solid-state drives that we are using all over the place. So why would you care about this presentation? So the first reason is that just learn how other best-in-class technologies use garbage collection. I still remember the times when some guys who were developing apps with not Java, they were saying, hey, but Java, it's like virtual machine. It generates a lot of the garbage. Then you need to dedicate CPU cycles to get things cleaned up from the memory, blah, 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 blah. But in fact, right now, if you look around, you'll see that Java is not the only one, and it's all about implementation. If you implement garbage collection properly, then it will benefit your technology. Second of all, you will understand where to look if you come across different performance drawbacks or latency spikes. Because if you check, let's say, the state of a JVM in your application and you don't see any symptoms, then the problem might be on the database level or hardware level. And today you will see at least what the reason might be. And final reason that is not on this slide, next time, whenever you have a conversation and someone asks you, hey, explain me the garbage collection in Java, how Java generates garbage, you can expand this topic to the level of the databases and to the hardware, okay? So my name is Denis Magda. I've been working with distributed databases and high-performance computing systems for the last 8 years. Presently, I'm with YugabyDB. That's a distributed SQL database that is built on PostgreSql. Prior to that, I was contributing daily to Apache Ignite. That's another distributed database, but it's designed for in-memory computing. Before databases and HPC systems, I was on the Java development team, building GVM and JDK at Oracle at Sun. So in today, I'm here on stage, but I took a friend of mine, Java Joe. You'll see this guy on the slides from time to time, because Java Joe is a principal engineer and architect who has been building Java application and services for over a decade. And right now, his current project is a pizza chain. He is creating a service for a pizza chain so that we can come to a pizza store, order whatever we like, or order this online. And Joe considers the following architecture. So he needs to create a RESTful, let's say, Spring Boot service. And that Spring Boot application inevitably needs to store and get orders from some database. He selected PostgreSql database to start with. And that PostgreSql database is going to use SSDs. Because SSDs are everywhere, they're cheap, they're fast, etc. And also the second version of the architecture that he can switch to later uses YugabyDB instead of PostgreSql. We will discuss why YugabyDB makes sense in some scenarios, but generally whenever you need to scale your PostgreSql database across cloud regions, when you need to deliver good latency across for customers around the globe, and blah, 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 then you will use YugabyDB, because YugabyDB is built on Postgres, it's easy to migrate. So this is what he considered. And then he created the first version of the application. The feature-wise, the service looks very good. It runs. It responds to the REST endpoints. But then, as a experienced developer, he decided to run a load test. So like he basically created a simple test. He loaded 1 million of records into this through the application, and then he executed a few million of updates and deletes. Once this test was over, he went ahead and checked the size of the database, and kind of he was scratching his head, thinking like, why the final database size notably exceeds the initial size of those 1 million records that I was using for the test, probably like 2 times or 3 times more the size of the 1 million records. And as an experienced and principal architect and engineer, he always wants to get the right answers. And starting from this point, he started looking what's happening beyond the Java application, like what's happening with PostgreSQL and what was happening with hard solid-state drives. So, and today we are going to look at the garbage collection of PostgreSQL, of YugaByteDB, of solid-state drives through the story of Java Joe, who was building that simple application, and then, as a curious engineer, he decided to explore what's happening in my surrounding neighborhood. And this slide, and usually when Joe started checking like PostgreSQL documentation, everyone knows like when would you use PostgreSQL or MySQL or Oracle? When you want to have a transactional database, the database that you can trust, where you can store your money, where you can store your orders, where you can store your subscription, everything, like when you need consistency. Those databases, they deliver one significant promise, that ACID compliance, atomicity, consistency, isolation, durability. And to support this promise, those databases have to implement so-called multi-version concurrency control, or shortly MVCC. So let's take this example. Why this MVCC is needed? Let's say that we always talk about Java applications that need to execute a lot of the, let's say, dozens and hundreds of customer requests in parallel. That's why we have all those virtual threads in Project Loom and blah, blah, blah. But then all of those microservices, Java microservices, they forward requests to the databases, and the database has to process also hundreds, if not thousands, of requests, selects, updates, and deletes concurrently. And MVCC is needed to make sure that all of those concurrent reads and updates, they always work with a consistent copy of data, so that you don't have any, let's say, dirty writes when one record gets updated before it was submitted, and that not updated record is being read by other transaction. So that's the goal of MVCC, to ensure that ACID guarantee is implemented properly. So let's take this example, simple example with our pizza chain application. You have this transaction number 1, and this transaction number 1 just begins, and it's going to read the value of the status column of your order. So presently, the value of the status column is ordered, meaning that the pizza chain is put in order, but nobody is baking it yet. And then before this value is read from the database, another transaction comes in PostgreSQL, and that transaction changes the status of the pizza order. So right now the pizza is being baked. But this order is not committed yet. The commit of the second transaction will happen a little bit later. Which means that when my first transaction wants to read this status value, it must not see this one, because this might never ever commit. This transaction might roll back, the server might crash. So this transaction has to see the current previous value of this order. And there might be multiple transactions of this kind. They're trying to read and write to the same columns and values of the same records. And this is when garbage gets generated in PostgreSQL. So we'll see it right now. So what Java Joe did, so okay, he studied this MVCC. It's really quick, it's easy to follow. And right now he wants to run an experiment. So like for his experiment, he extracted one of the tables of his service. That table is pizza order. We have just, primary key, we have the status, and we have order time. When it comes to the status, there are going to be 4. Pizza is ordered, pizza is being baked, pizza is being delivered, and yummy in my tummy means that pizza is delivered to the customer and hopefully consumed. So then Java Joe asked me Denis, once you're on stage, just walk the guys through these slides and explain them how like the garbage gets generated in PostgreSQL. But we will take a different approach. I will show you what exactly was done, because it's better to see how that stuff is happening when it's possible. So let's do this. This is our simple RESTful application in Java. It uses Spring Boot. Here is I have a orders controller where we can put in new order, we can change status, we can change order time, we can delete it, all the typical stuff that we usually do. We also have here a repository, just the data model object, blah, 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 all that casual, like all those casual classes. And right now what we want to do, and that version of the database first is going to work with PostgreSQL. So let me connect to my PostgreSQL instance first. So right now when I check, I have some other tables because I use Postgres all the time. I don't have the pizza orders table yet. What we need to do, we need to start this application. So the application that I just showed to you, let's run Spring Boot command. And our application is going to be ready for the requests. So the application is running. Let's go back to PostgreSQL. Check that application, once it started, yep, it should have created this pizza orders table. The pizza order table is here. But if you check what's inside, you will find nothing. Pizza order. It's empty, okay? And now we are doing the test. Let's say that we have this API endpoint. The service is running. I want to put a new order in, and I'm assigning an order ID of 1. So let's add this order. The order is in the system. We can double check. Let's go to the Java application. Yes, you can see that my spring method was eventually converted into that insert statement, and the order is in the database. So let's go back to Postgres. So on the Postgres side, we can see, yep, the pizza is here. And also Postgres, actually, one of the reasons why PostgreSQL is becoming so popular, the rank of the Postgres is going through the roof when compared to other relational databases. It has extremely feature-rich ecosystem of different tools and frameworks. So by default right now, for me, it's extremely easy to look inside of the Postgres. So let's look in the memory of the Postgres, in the pages that store that physical, the data physically. So for that, I'm going to use a special function. It's called Heap page. I created this function using pginspect inspection. So what it requires you to provide 3 parameters. First, the name of your table, and then the range of the pages that you want to look in. So right now, I just have one single record, which means that I definitely Postgres uses just one page in memory. So that's the state of the memory. So this is my record. This is the physical location of this record in the page. And here is, pay attention, we're going to look at from time to time at these 2 columns. This xmean column has this number. This number is the ID of this transaction. That operation that we sent through the Java application and that was eventually executed by Postgres had this transactional ID. And this xmean means that this transaction was added to Postgres by, like at this time, by this transaction. Xmax will keep the value of a transaction that will delete this record. It's 0 right now because nobody is trying to delete this record. It's here in the database. So now let's talk about the garbage, and let's talk about garbage collection. So what's happened next? The order is in, and finally there is a chef who is ready to bake this pizza for us. So which means that our RESTful application receives the next request. Let's change the status. So when it comes to the status change, first my order ID was 1, and before it can be delivered, it needs to be baked, right? We are changing it to baking. And I'm sending this to this change status API endpoint. Okay, looks like everything went well. Let's check with the application log file. Yep, you can see that we updated the record. Now, usually what we do when we write our code, we don't need actually to focus on the internals, but let's say that I want to execute, let me check. This is what the applications will see. This is the record. the status of the pizza order was updated. This is what we've done. But now, let's look inside. Let's see what actually is stored in Postgres. You see, 2 records. Instead of 1, you have 2 copies of the record. This is the first version of the record that we inserted. And right now, look at this Xmax value of this record. It means that this record is marked as deleted. And it was deleted by this update operation. And the same update operation inserted a new record into the Postgres storage. So in fact, when you are talking about Postgres, and in Oracle, MVCC is implemented a little bit differently, but also in Oracle, you will keep the old versions of the records to, like within some time frame. You will have these copies. You will have the copy, the extra copies of the data. So now let's see that the order is being sent, is ready, and we want to deliver it. It's being delivered. And finally, let's check actually what's happening. Let's check in the memory. Now I have 3 copies of the data. I changed the status, and another copy is being created because the other 2 versions still might have been used by other transactions, or nobody longer needs those 2 past versions, but still they will be garbage collected later. Finally, the final test, what do you think would happen if I want to update the status for this order the last time? The last one is a yummy in my tummy, which means that the customer got this, all right, all is good. And now let's check first the table, this one order with the latest status, but inside you have 4 versions of the records. And this is the last one. This last one keeps the latest version for this yummy in my tummy. But the last 4 are here. So this is the garbage, right? And how do we deal with the garbage? In PostgreSQL, we have a garbage collector, but it's named differently. It's not called garbage collector, it's called vacuum. Vacuum is a special process that Postgres starts on your machine, and that process goes through the memory of the database, finds all of those, let's say, removed or deleted records, and eventually either, most of the time, it basically frees up that stale space, and so that it can be used by future data, for future data that you're going to put or update in the database. And sometimes it can also compact your database, but the compaction usually requires, advanced locking on the database side that can block your applications. So let's quickly look at this using the graphics, and then we are going to run a few samples. So let's say that there are 2 types of vacuum in Postgres. We have the standard vacuum that runs concurrently with the database, and that will definitely remind you of the garbage collection in Java. We also, our garbage collectors like G1, CMS, etc., or Azul C4, they run concurrently. They don't block your application. And this standard vacuum operation, it's basically, it doesn't do a lot of compaction most of the time. But let's say this is a block of memory in Postgres, and these pages are used with your data. And this is live data, it's live and you're going to use it, it's valid. But this area in the memory and on disk is dead, you need to remove it. So then, once in a while, the AutoWagon starts, and it basically will get to this page, and it will keep these pages untouched, and the dead ones, they will be marked as free, and a special free map structure in Postgres will be updated, and then whenever you insert a new data or you update a new data in Postgres, those free pages will be reused. So at least you will not be running out of memory in Postgres. So it's same as in Java, it's very well thought through. But also there is a full vacuum operation. Most of the time, IT administrators no longer use it, but sometimes you, especially when our applications, let's say, have to operate 24/7, after like full vacuum, is not the best kind of thing in your toolkit. But let's see like how AutoWagon works. It does the same operation that is done by the standard vacuum, but also it will try to compact your live data. For instance, the same, let's say, page that we have, and then these dead records are removed and the live pages are moved to the earlier addresses in your page. So this way you're getting the free space in the end of your memory, like in the end of your disk files. And then if needed, this space can be returned to your operating system. So this is what can happen. So let's run standard vacuum. Let's double check that still probably, because I think that every 15 minutes by default Postgres starts AutoWagon, but right now like I just have a few records and doesn't make sense to waste resources. You can execute vacuum like programmatically in Postgres. Let's emulate it. Let's say that I run this vacuum command. It's standard vacuum. It doesn't compact the data. And right now, when you look into the state of the memory, you see that this is my actual record that is visible, that will be used by all the future requests. And this is the space that was used before, but right now it's unused. And this status means that this page is referenced from the primary index, from the B tree. And if you're doing this search through the index, like select from pizza orders where ID is equal 1, the request can go through the index. And the index references these pages. When the request comes from the index will see that, all right, this actually location is empty and you need to go to this location, to location number 4 to get the data. It's like internally used by the Postgres B trees and the space that that stores your data. So now, but this space can be reused. It's not compacted, it can be reused. Let's run this experiment. Let's say that once that pizza was delivered, I have another API endpoint. It's called a change order time. Let's try to change order time. And now, as you know, when you update a record in Postgres, then a new version of the record will be generated. And my assumption that when that new version is going to be generated, I want Postgres to reuse that space that was cleaned a minute ago. Change order time. We are changing order time. So that's the ID. And I need to change order time. Today's order time. And today's 2022. It's September 27th, and let's see, 11:45. All right, looks like yes, I didn't do surprisingly no mistakes. And now let's execute this command. Yeah, the time was updated. And if you look into the state of the heap, you see this position was reused. So this space was reused by Postgres. So sounds familiar, right? In Java, also when garbage collector runs concurrently, it doesn't compact data all the time, but at least it can clean the dead space, and then that just freed space can be reused by future data, by future objects. Postgres does the same. The only difference is that Java is a platform and programming language and environment, and Postgres is a database. So, but let's do the final check with Postgres here, and then we will move forward. How about deletes? What if I want to delete an order? Because delete also, it's not like that, it doesn't happen in place. Similarly, we need to comply with MVCC, and the record will be just marked as deleted, and only later it will be garbage collected by the vacuum. So for that one, I guess let me recall the endpoint. It's called delete order endpoint, and so this is my order. The order ID we still need it. This one we don't need. And what else we need? I need to change order time to delete order. Delete order. Error method not allowed. Why method is not allowed? Delete order by ID. Let me check. Probably I misspelled something. Yeah, because I need to change this command. It's not a put operation. It's a delete, HTTP delete operation. So now it's good. And now if we go to Postgres, nothing here. But the Postgres is still full a lot of the copies. We have this. This was our latest copy when we changed the time, and right now it said that it's deleted. I don't have any live data. And when you run full vacuum actually is going to basically rebuild the table from scratch, and it will take the space, it will compact the data. So if we do this vacuum full right now, it will take more time, and you will notice it. But generally, in the end of the world, you will have just free memory space, and you will not have any data on disk for Postgres. So let's check the heap. It says that this heap number out of range because it was fully compacted, no any data. So full vacuum for you is like stop the world pause in Java. When let's say Java JVM kind of cannot longer efficiently run garbage collection cycles concurrently, then it will eventually stop your application and it will kind of start garbage collecting and compacting the data. Postgres does the same. But you don't want Postgres to do this with your applications because let's say your application request will be blocked for this data, for this table. All right. So that was Postgres. So here is generally recommendation, right, by Java Joe, who created this app and who wanted to explore what happens with the database. Always do the load test of the application plus your production database. Don't just do this with your embedded database. I know that sometimes when we use different ORM frameworks, they come with embedded databases. Take your database that you're going to use in production on that hardware and test it. Do the load test. If you use Postgresql or any comparable relational database, don't touch those AutoWagon settings unless you are sure that you need to do them. But if during your load tests you discover that, okay, so something needs to be tuned with Postgres because Postgres generates a lot of the garbage and sometimes my queries get paused significantly, then either find and talk to your DBAs, the guys know how to deal with the databases and how they can be tuned. Or if you are in the cloud, you can always review and consider the database managed options because all of those databases are managed by the cloud providers and different vendors, and they will be taking care about these different GC-related things. So finally, Java Joe was happy with the first version of the application, but as I said, he's creating a pizza chain, not a pizza shop. The goal of a pizza chain is to operate across several locations, meaning that probably the first year, that's going to be just one pizza shop in one state, but over the time he wants this company to operate nationwide. And when that time will come, they need to be able to scale. You know that it's easy to scale at the application layer, right? You can deploy multiple instances of the applications. You can deploy global cloud load balancer, but then you also need to scale your database. As long as he selected PostgreSQL for the beginning, then for him, once the time comes, he can easily migrate to YugabyDB. Just a couple of slides about YugabyDB, and I will start pitching this database. YugabyDB, basically, if to split it into halves, it comes with the query layer and the storage layer. Every database has those layers. The query layer is basically PostgreSQL. It's the PostgreSQL source code that is modified. And below, we have the distributed storage layer. It's like a distributed database. The storage layer was inspired by Google Spanner. Google Spanner, I think, was, in fact, if not the first, but at least among the first truly distributed relational databases. The only one disadvantage is that it's available only in the Google Cloud infrastructure. So how YugabyDB is compatible with PostgreSQL? So just this picture in blue. Everything is what you see in blue is the query layer of Postgres, and it's basically what we use at Yugabyte. And what we've done, we enhanced a few components such as optimizer, planner, and executor, so that those components know how to execute queries across multiple nodes, across a multi-node cluster. And why, again, as a short summary, when it's used, if Java Joe wants his pizza chain to withstand cloud outages, so his application layer is good, and database also will be able to do that because you can deploy your database across multiple availability zones or regions. Then if, let's say, you have customers in the West and Chicago in the East, then the latency time can be low because you can store data close enough to your customer base. And then if the pizza chain ever goes, let's say, across the borders, if, let's say, someone decides to open this pizza chain shop in London or Tokyo, etc., it's going to be easy to do this with this architecture. So now, This is a difficult slide, the most difficult slide, but I'll try to translate to it you like the simplest way possible. So PostgreSQL and many other relational databases, especially single node databases, they use B+3 as a data structure. Like when you create an index, it uses B+3. Distributed databases, including YugabyDB, Cassandra, and many others, they use log-structured merge tree. So how it works? Let's say that I have some write operation. My application inserts a new order into the database. So this write will be written to a write-ahead log file, so that if your database goes down for any reason, you don't lose this update. And this write is also written in memory, in mem table, so-called mem table. Mem table, from the data structure perspective, that's a red-black tree, so you can update it in place. And then this mem table has, let's say, some constraints. It cannot grow. It can grow to a certain size, but then once, let's say, it goes beyond that size, it needs to be flushed to disk. So it's first how that flush happens. The mem table is marked as immutable, so no any writes happen to this mem table. A new mem table is created for all of the future writes, and then this immutable mem table is written to disk in the form of the SS tables. And these SS tables are immutable as well. They are basically ordered. For instance, let's say we have these orders. Every order has integer ID, 1, 2, 3, let's say 1,000, etc. This SS table and every SS table keeps a range of your key. For instance, the first SS table will keep orders from 0 to 500, this one from 500 to 1,000, and go on, go on, go on. So there might be multiple versions of the same record, because YugabyDB is similar to Postgres. It has to store multiple versions of the record for the sake of ACID guarantees. And it can happen then you have the same record, but of different versions in mem table or immutable mem table as S table. And it can happen, let's say that I have one version of my order here when it was ordered, then I have another version of this record on a different level of this structure. But this data structure also has its own garbage collector. It's called compaction. So this is a process that runs continuously. So what the process does, it scans, it takes, let's say, two SS tables like here and merges them. During the merge operation, you are creating a new SS table that is written to the next level. And during that merge operation, all of the duplicates, let's say the old versions of the records, are removed from disk. And so this happens continuously, and this happens all the time, so that your disk consumption, is kept to some reasonable size. When it comes to read, it's always said that with LSM-like data structures in databases, you might deal with read amplification. It's like when you read and you need to read from multiple places. It can take place, but usually you don't read that much, and the read can be relatively fast. For instance, you want to read in order, and first that read will go to the mem table. If it's not in mem table, then we will read from the latest immutable mem table. If it's not there, then it will read from the SS table that is in the range for this ID. So let's take this example. I have one of these SS tables on disk, and let's say that Java Joe selects he wants to get all the orders which ID is between 500 and 505. So the database will quickly locate that SS tables that keep these ranges, and it can sequentially quickly this is just one read block, one read operation from your SSD, and then you're getting these records and something else, and then you can filter out and return whatever is needed to your application, okay? So now let's see how it works with YugabyDB. Quickly, we will take this example. So let me actually for YugabyDB do this. Because in Yugabyte, we don't have, this is a different data structure, and we don't have that view into the state of the memory. It's just designed differently, LSM trees. But there are some tricks that will allow us to see that multiple versions are in fact generated. So let's create Postgres. So here is, let me quickly find all right, this is what we did, this is what we did. So now let's connect to YugabyteDB. I don't have any tables yet, which means that actually, yes, from the application standpoint, let me quickly stop this application. We need to switch the application from Postgres to Yugabyte. I have the properties file. So what it means, I basically just, I'm using even the same driver, PostgreSQL driver, but different connection endpoint. And this is what we don't need. Okay, done. So now let's restart the application. And the application is running. Let's put a new order. We'll do it quickly right now. Okay, looks like the flight is normal. The application can work with YugabyteDB with no code changes. So now let me change for this order the status a couple of times. I'm changing it to baking, and I'm changing it to delivering. And next, when you check what's in YugabyteDB, you certainly will find only one record, same as in Postgres. But in fact, we have multiple versions stored internally in that LSM tree. So let's use, some hardcode techniques to figure that out. First, I will be connecting. I'm running YugabyteDB in Postgres in the Docker. Let me connect to the Docker container of YugabyteDB. That's a single node cluster. So there, I'm going to the bin directory where I have some tools. And next, let me copy and run this command, and then I will explain you what happens here. What I did, no, I'm not here. So where am I? pwd ls. Let's try again. Docker, yeah, we need to do this. Now we are in the Docker container. So we are going into the bin directory, and let's run this command. So the command prints the ID of the pizza order table. That's internal one. Don't repeat this at home. And next operation, I'm flushing this table. I'm flushing the mem table, because right now how the data is stored, the full copy of the data is in mem table in memory, and all the other stuff in the write-ahead block file. But right now, I just forcing YugabyteDB to flush this mem table into SS table on disk. So I want to show you those multiple versions. So let's flush the table. It's flushed. And now the most cumbersome operation, which we need to change. So what was my so let me run the table ID. I need table ID, and this is my command. So my table ID, I need to insert it here. All right, that's a long command. This is what happens when you're trying to hack a database. And tablet ID, we will find it this way. Autocomplete feature. All right. So we've got, some scary numbers, but let's do it this way. So this is what we've got. So we are looking at column number 1. Let me do it this way, guys, so that it fits the screen. All right. So we are looking into the column number 1. We have 3 versions. And you see that the value of this column is different. That was when the order status was ordered. This was when the status was baked. and this one when the status was delivering. So like we inserted this order, and then when we updated the status column 2 times. So this is, just what happened. This is how it's stored in the SSD table. Then all the time, it's going to be compacted, and in this SSD table, we will have only just one version of this column. So what's the difference between Postgres and Yuga by DB? Yuga by DB stores versions not for entire record like Postgres does. It stores versions of columns that were changed. But here is my question was, and Java Joe also highlighted this, what the heck? Dennis, you were updating the status column, but what is this? Why the second column order time? Why do I keep the different versions for that column? And turns out that's Spring Boot. So generally, when you use in this application, let's look how I update the records. I actually didn't care about performance. I just get this pizza order and I change the status of this pizza order and I use the save command. And what the save command does, it updates both values, which means that Yuga by DB will assume that you also change the order time. So what it means when you're dealing with distributed databases that use LSM trees that can keep different versions of the columns, don't use save command of Spring Boot or like comparable frameworks. Just update, specify to your ORM what column you want to update so that you can save more space, okay? Because here is, in the example with Yuga by DB, you see that we wasted, for no reason, the space for this order time column. Because in fact, the same value, you see, no differences. Right. Enough about databases. Enough. And with Yuga by DB, the idea is similar. Recommendation is the same. If you use Yuga by DB or another distributed database, again, well enough load testing on the hardware that you're going to use. If you see any performance spikes, if your application gets stopped and you don't have any symptoms on the Java side, take a look at the database. It might be that you need to tune compaction or do something else. So, final one, SSDs. We have 8 minutes left, and right now we will talk about hardware. Because Java Joe was happy. He learned something new. So right now it turns out that garbage collection is so wonderful technique that is used successfully by the databases that he selected, and he is confident in taking and using this application. But then he ran an extended test for multiple days on the real hardware, and then all of the time he saw sudden performance drop, throughput drop, and he had kind of no clue, no reason. He kind of knows how to start debugging. He checked the application, everything looked normal, the database was fine. And what's happening? The only one hint that he got, his SSD disk was 80% full. And then he started searching, like, what's happening? Like, why my SSD utilization went 80%, but my performance and throughput dropped significantly, dramatically. And then he goes, come on, and SSDs also use garbage collection. So what happens with SSDs? So let's say that you're writing a block of data, let's say those orders from, like Postgres eventually decided to write data to into the block. And in SSD's level, SSD operates on the notion of blocks. That's block is like consists of multiple pages. And a page is, by default, page size is around 4 kilobytes. So like you have a block and you have multiple pages in this block. So when you write to SSDs, you write pages, right? And you write your new data, and the data will be always written to a new page. The data cannot be overwritten. It's always written to a new page. So which means that when you update your block and SSD, so a situation similar to PostgreSQL or Yuga by DB happens. So what SSD controller does, it will find the previous version, let's say, of this block or data, it will mark it as stale, and then it will write the new data into the new free page. And then once this operation update is completed, in fact, you will have this state of this block. The first, let's say, page is stale, it's not used. This data will never ever be addressed by your operating system application. And this one contains live data. So over the time, the garbage gets generated, because if our application, if our Java application, that takes orders, change the statuses, asks Postgres to update the statuses, Postgres eventually will be sending all of those updates to SSDs. And this is what we are going to get on the SSD level. So the question is then, like, why SSDs don't erase data in place? For instance, if SSD knows, then this page is stale, nobody is going to use this data. Why SSD doesn't basically erase it? The thing is, in physics, when you erase data in SSDs, they put a different amount of voltage, and with that amount of voltage, you can damage data in the nearby pages. So for instance, let's say that SSD wanted to erase this page, and then because the voltage was high, the data in these nearby pages was erased and damaged. You don't want this to happen. That's why by design, when you want to erase SSDs, it erases the entire block. You just need to remove this whole block. But before you can clean this block, because right now we can see that this block is becoming useless. Half of the block contains dead data. So what a SSD does, it also has a garbage collector. And while in Postgres it's called vacuum, in YugaByteDB it's called compaction, in SSDs it's called garbage collection, similarly as in Java. So how it works, let's say that you have block number 1. This is what we have right now. And then first step, the garbage collector needs to move live data to another block. So let's say we have block number 2. All the data, all this live data is moved there, and then SSD controller goes like erase, and it erases this block number 1. So this is what's happening. And then this block number 1 can be reused in the future. And this repeats over again and again and again. But we all know in Java, if we want Java GC to run concurrently and have negligible or no impact on our application, we need to provide enough CPUs to garbage collector, and we need to provide some free memory space, right, for the job of garbage collector. And in the SSD world, manufacturers, what they do, when you buy an SSD that, let's say, comes with 100 GB in size, in fact, manufacturer put aside, let's say, extra 28 gigabytes for these internal needs, for the garbage collection, etc. So it's called over-provisioning, factory set over-provisioning. And this space is reserved for garbage, for SSD just to, to function, to find some trade-off between speed and the size. And also actually, SSD, if your, let's say, disk, your space, right, that is given to you is free, then SSD GC also will be using this space as well for the GC needs. But generally, what usually happens, you can see the throughput and performance of these SSDs they show rating once their usage goes beyond 50%. So this is why recommendation again by Java Joe. Similarly, when it comes, if you want to validate your hardware, for the hardware, you need to run an extended test, like run it like for at least a few hours and probably just put a good load and check like if you have that performance drawback. Because I was personally involved in several projects we were building, the guys were building high performance applications, and they witnessed this multiple times, like when SSDs were the reason. And then keep an eye on the SSD utilization and performance, because if you see that the SSD utilization goes, let's say, to some critical value like 80% or 90%, it's inevitable that your performance will be impacted, because SSDs, they will start slowing down your request because they need to clean the space for your upcoming data. All right, but anyway, that was the happy end for Java John. His pizza chain right now operates in several locations in the country. He learned something new, so right now he knows that garbage collection successfully implemented and used not only in Java, but in the world of databases and hardware. And this is just a justification that if it's all about, let's say, doing things the right way, those probably, I do believe that there were many attempts to use garbage collectors and to create GVMs, right? But many of them failed. But Java, Postgres, and SSDs is the justification of that you can create a first-class, best-in-class products that use garbage collection and they deliver the performance and scale and whatever we need. All right, what if you want to learn more? If you wish to learn more, I usually start with the books. I love reading books. If you want to see how to design data-intensive applications, some different concepts, check this one. architecting for scale is ideal for those who build those high-load applications, and the high-load applications can be commerce application, transportation, doesn't matter. Check this one, it's created for the cloud. If you wanna look into the databases, which is, the ocean, but this book is for you. It's written by for developers, database internals. It reviews different database architectures, and MVCC and many other concepts are discussed there. Take a look. If you want to learn more about distributed SQL, you can pass and check Yugabyte University. All the courses are free. And if you have any questions to me about this presentation or anything about, let's say, Java plus databases, Java for high-load distributed applications, you can find me on Twitter, Denis Magda, my surname, single word, and thanks for coming. Hope it was useful. All right. Any questions?
Does Yugabyte operate on files, or does it operate on direct block access?
It operates, so Yugabyte, let's take an example, like one node cluster, one node. Every node will have a write-ahead log file. That's a file, it has to be. And those SS tables, they're files. It's like they're stored in some location, and this is actually what I was doing today with those, let's say, hard-to-digest commands. I was trying to open specific files and find the location in those files for that version. And then you have this architecture, and when you deploy a multi-node cluster, 2 or 3 nodes, is basically the same. Every node has its own write-ahead log file, its own files, but every node keeps a subset of your total data, of your user data. All right. If any other questions, just catch me here, and don't miss the lunch, right? Get some energy. Thanks.